The most significant piece of evidence that we have in this entire ancient astronaut puzzle is Puma Punku in the highland of Bolivia.
In the windswept highlands of western Bolivia, just beyond the southeastern shore of Lake Titicaca, lies one of the most technically perplexing archaeological sites in the Americas. Puma Punku, a monumental stone platform associated with the ancient Tiwanaku civilization, has challenged archaeologists, engineers, and materials scientists for more than a century.
We have had some circumstantial dating, but we have been unable to date the stones of Puma Punku themselves. They could be thousands, if not hundreds of thousands of years old. We don't know.
Its fame does not rest on size alone, but on precision. The site's signature H-shaped blocks and massive sandstone slabs display geometric regularity and joint tolerances that appear at first glance incompatible with conventional narratives of early medieval construction. For decades, these stones have been used as evidence in sweeping claims about lost civilizations and vanished technologies. Yet recent advances in 3D scanning, digital reconstruction, and laboratory analysis have shifted the discussion away from speculation and toward measurable data. What has emerged does not require supernatural explanations, but it does demand a far more sophisticated view of ancient Andean engineering than was once assumed.
These are the mysterious ruins of Puma Punku, nearly 13,000 feet in the Altiplano of Bolivia.
Puma Punku sits on the Altiplano, a high plateau more than 12,000 feet above sea level. The environment is harsh, oxygen is thin, temperatures swing dramatically, and seismic activity is common. Any large construction effort here would have required careful planning, durable materials, and a deep understanding of how stone behaves under stress. The builders of Puma Punku were not improvising. They were executing a system.
Ancient Incan legends that suggest that they had the capability of softening the stone.
For generations, villagers repeated that tale.
The site is closely linked to Tiwanaku, one of the most influential pre-Columbian cultures in South America. Archaeological and radiocarbon evidence places the major construction phases of Puma Punku between approximately AD 500 to 36 and 600.
Archaeologists are baffled by what Puma Punku was, how it looked, and what the purpose of this enormous structure would have been.
These dates do not come from the stones themselves, which cannot be directly dated, but from organic material embedded in the engineered mound filled beneath the platform. Charcoal, plant remains, and bone fragments recovered from these layers have been analyzed in multiple laboratories, producing a convergent timeline that situates Puma Punku firmly in the early Tiwanaku period. This chronology matters. It places the site in a context of rapid architectural and ceremonial expansion across the region. Tiwanaku was not a marginal society. It was a complex, state-level civilization with long-distance trade networks, advanced agriculture, and monumental urban planning. Puma Punku appears to have been part of this early surge, possibly serving as a ceremonial gateway or ritual platform connected to the larger sacred landscape. The stones themselves are what draw the most attention. The iconic H-blocks are carved from andesite, a dense volcanic rock known for its hardness and durability. Each block is defined by a repeating modular geometry: right angles, parallel slots, recessed channels, and projecting tabs that allow blocks to interlock in 3 dimensions. This is not decorative carving, it is structural design. When examined closely, the joints between these blocks are remarkably consistent. Even where centuries of weathering, earthquakes, and human interference have taken their toll, many surfaces still meet with gaps measured in millimeters. This precision has fueled claims that the stones were machined or cast rather than carved. For years, such claims remained largely speculative, unsupported by comprehensive measurement. That changed with the application of high-resolution digital archaeology. Beginning in the late 2000s, researchers used photogrammetry, terrestrial LiDAR, and drone-based scanning to capture every accessible stone at Puma Punku in 3 dimensions. These scans, accurate to within a few millimeters, produced detailed digital models of individual blocks. When these models were analyzed and virtually reassembled, a clear pattern emerged. The blocks were not unique one-off sculptures. They belonged to a standardized system. Teams at institutions such as UAC Berkeley created scaled 3D printed replicas of the H blocks based on these scans. When assembled physically and digitally, the pieces fit together cleanly, confirming that the original builders worked from repeatable templates rather than improvisation. Gravity simulations showed that when properly aligned, the blocks naturally settled into stable configurations, distributing load across multiple contact points. This modularity explains how the platform could resist seismic forces common to the Altiplano. The foundations beneath the platform reinforce this interpretation. Large red sandstone slabs, some weighing more than 100 tons, were set into carefully leveled trenches keyed into the bedrock. In several locations, these foundation stones were joined using tongue and groove techniques that prevented lateral movement. This is not a casual solution, it is a deliberate response to an earthquake-prone environment. Adding to this structural logic is the use of metal clamps. Archaeologists have identified sockets carved into the stone surfaces where metal staples once held adjacent blocks together. Traces of bronze remain in some joints. Metallurgical analysis shows these clamps were made from copper-tin alloys containing arsenic, consistent with known Andean bronze technology. These were not decorative additions. They were reinforcements designed to bind stones under stress. Together, the interlocking geometry, keyed foundations, and metal clamps form a coherent engineering system. Each element addresses a specific challenge: weight distribution, seismic stability, and long-term durability. When viewed this way, Puma Punku does not represent inexplicable perfection. It represents intentional design executed with remarkable skill. The question that remains is how the stones were shaped. Traditional explanations hold that Tiwanaku masons carved the blocks using hammerstones, abrasives, and bronze tools. Andesite is difficult, but not impossible to work with such methods, especially over extended time frames. Experimental archaeology has shown that precise stone carving can be achieved through repetitive grinding, measuring, and fitting. What makes Puma Punku unusual is the scale at which this precision appears to have been applied. This is where laboratory analysis has complicated the picture. Recent studies using scanning electron microscopy and X-ray diffraction have examined thin sections of the red sandstone blocks at Puma Punku. In several samples, researchers detected amorphous binder phases and elevated concentrations of sodium carbonate, also known as natron. This chemical signature does not match nearby natural sandstone outcrops. Instead, it resembles artificially consolidated stone produced through geopolymerization, a process in which mineral aggregates are chemically bound into a solid mass. Geopolymer technology is not modern in origin. Variants of it are known from ancient Egypt, where natron was used in mortars and construction. The hypothesis proposed by some researchers is that Tiwanaku builders may have produced a castable stone by mixing local sand, volcanic ash, and a sodium-based activator, pouring the mixture into molds and allowing it to harden. This would explain the uniformity of block faces, the sharp internal angles, and the absence of clear chisel marks on some surfaces. Laboratory replication has shown that stones produced using such methods can match the density, durability, and microstructure observed in some Puma Punku samples. Under the microscope, these artificial stones exhibit amorphous phases and bonding patterns distinct from sedimentary sandstone formed over geological time. The andesite H-blocks present a more contentious case. Andesite forms at high temperatures that should destroy organic material. Yet in 2019, one laboratory analysis reported nitrogen and carbon signatures within thin sections of the andesite blocks. These elements could indicate the presence of an organo-mineral binder, potentially derived from plant or animal materials mixed with volcanic aggregates. If confirmed, this would suggest a sophisticated casting process previously undocumented in the Andes. However, this claim remains controversial. Critics argue that the detected signatures could result from surface contamination, soil infiltration, or analytical error. No independent multi-laboratory replication has yet conclusively verified the presence of ancient organic binders within the andesite. Recognizing the stakes, researchers have proposed a rigorous blind testing protocol. Microcore samples from multiple H-blocks are to be divided and distributed to independent laboratories under coded labels. Each lab will conduct SEM, EDS, and organic compound analysis without knowledge of sample origin. If organics are detected, they will be radiocarbon dated using accelerator mass spectrometry. Only if results converge across laboratories and align with the established Tiwanaku construction window can the casting hypothesis be considered credible. As of 2025, those results are still pending. What is already clear is that Puma Punku's builders achieved a level of consistency and structural logic that rivals many modern masonry projects. Digital reconstructions by ADA lab teams between 2024 and 2025 have confirmed that the site's scattered stones, when properly oriented, form a coherent T-shaped platform with symmetrical gateways and repeating modules. Machine learning analysis of these reconstructions has identified proportional systems and symmetries consistent across the site, reinforcing the conclusion that the monument was planned as a unified whole. It is also important to acknowledge how much of Puma Punku's current chaos is modern in origin. In the late 19th century, railway construction crews dynamited sections of the site, toppling and breaking stones to use as ballast. Entire blocks were removed or split, destroying their original context. The disordered appearance that fuels many speculative theories is, in large part, the result of this destruction. When stripped of exaggeration, the story of Puma Punku becomes more impressive, not less. It reveals a civilization capable of standardized design, advanced materials knowledge, and long-term planning in a challenging environment. Whether the stones were carved, cast, or produced through a hybrid process remains an open scientific question. What is no longer in doubt is that the builders understood geometry, load transfer, and material behavior at a high level. Puma Punku does not require lost super technologies to be remarkable. It requires recognition that ancient societies were capable of innovation that modern observers often underestimate. As laboratory testing continues and digital archaeology refines our understanding, the site stands not as evidence of mystery beyond science, but as an invitation to apply science more carefully. The stones of Puma Punku are no longer silent. Through measurement, modeling, and controlled experimentation, they are beginning to explain themselves.